Good day, class. So our focus for this set of slides will be now mass transfer in various geometries, or specifically mass transfer coefficients in various geometries. Now we'll be looking into the use of the dimensional numbers, the Smith number, the Stanton number, the Sherwood number, and even the Reynolds number first in establishing the kind of flow, whether it's laminar or turbulent. Then from that, we can apply the necessary or the appropriate equation for a particular geometry after we have already considered the type of flow. So this is mass transfer, again, coefficients in various geometries. Now, the first part of this set of slides will be discussing dimensionless numbers that are used to correlate the data that are given in the problem. So after this, then we'll go to the actual equations that we will be utilizing together with the appropriate illustration or graphs that will solve what the problem requires. Now, the experimental data for mass transfer coefficients obtained in various kinds of fluids and even different velocities and different geometries are correlated using the dimensionless numbers that I have mentioned. So on top of the list is Reynolds number, which actually tells us whether the flow is laminar or turbulent. Now in this formula, we have L as the diameter for the sphere, if the shape is a sphere, and L is the diameter of the pipe if it's a pipe, or L is really the length if we're considering a flat plate. So the L in here depends really on the geometry. So if we have a sphere and if you have a cylinder, then your L here will be the diameter of the sphere and the diameter of your cylinder. If it's a flat plate, then it's really the length of the flat plate. Now, the velocity is the mass average velocity in the pipe. Mass velocity in the pipe. And rho is the density of the fluid. And of course, the same thing with the viscosity. Now, in a packed bed, the superficial velocity, that's the V here, which is represented by V prime, is the empty cross-section of that particular packed bed. And sometimes you also use this particular, or most of the time we are using this particular V prime, but we are to convert it to V before we substitute it in this particular dimensionless number. So determine, in the case of packed bed, determine first the V prime is given in the problem, then solve for the actual V, which is the mass average velocity of the fluid inside the pipe. Now, you will be needing the void fraction. So that's the epsilon, the void fraction of the bed together with the empty cross-section velocity. That way we can have the actual mass average velocity that should be substituted to this particular formula. So that's for the Reynolds number. Now, dependent again on the geometry of the solid wherein our fluid is going to pass through. Now, we have another dimensionless number here, which is the Smith number. It's also dependent on viscosity and density, but aside from that, it's also using the molar diffusivity. Now, dependent on the kind of material that is going to diffuse through our fluid that is flowing on the specific geometry that is stated in the problem. Now, the viscosity mu and the density rho used are actual flowing mixture of solids A and fluid B. So the viscosity and the density that is to be used in the Smith number is actually already the property of the mixture, that of the solute that diffuse through the fluid B. If the mixture is dilute, the properties of the pure fluid B can be used, which is most of the time simply just water. So if it's a very dilute solution or a dilute solution, then the mu and the rho of the mixture of solute A and B will simply be the properties of your solvent B. Or that's your fluid B. Now, the Prandtl number, which is the ratio of the product of the Cp and the mu with K for heat transfer, is actually analogous to this Smith number for mass transfer. So the equivalent of mass transfer Smith number in heat transfer is our Prandtl number. Now, the Smith number, actually, the one that we just discussed a while ago, the mu over rho DAB, is the ratio. So, it's the ratio of the shear component for diffusivity. So, that's your mu over rho to the diffusivity for mass number. So, ratio of the shear component for diffusivity, which is mu over rho, to the diffusivity for mass transfer, which is the molar diffusivity. And it is physically relating the relative thickness of the hydrodynamic layer and the mass transfer boundary layer. The relative thickness of our hydrodynamic layer and the mass transfer boundary layer. Now, the third type of dimensionless number is the Sherwood number, and given by the formula K sub C prime times L over DAB, and it could also be expressed in terms of this or in terms of this, depending on the convective mass transfer coefficient that is given in the problem, which we have discussed in the previous example. Now, it says here that your substitutions will be based on what's available in table 7.2-1 in terms of the formula and the actual given in the problem. So, that's for the Sherwood number. Now, the fourth is the Stanton number, which is n sub st, and is still dependent on the convective mass transfer coefficients. And this time, you get to see a new parameter, which is the G sub m, which is the product of the average velocity, the rho, the density, and the average molecular weight, which is also equal to the average velocity and the concentration. Now, often, the mass transfer coefficient is correlated. So, the mass transfer coefficients that appear in these last two dimensionless number, the Sherwood number and the Stanton number, are correlated by a dimensionless J sub D factor, which is related to K sub C prime and N sub S8. And that J sub D is actually equal to, again, you have the appearance of the convective mass transfer coefficients together with these two last dimensionless number. The Sherwood number, you have the appearance of the Sherwood number here, and you have the appearance here of the Smith number. In here, you have both the Sherwood, actually three dimensionless number, the Sherwood, the Reynolds number, and the Smith number. So this is what we call JD factor, dimensionless also, that relates the other dimensionless number to one another. So this is how they are related. So, but the main dimensionless numbers that we have the option to use depending on what's given in the problem are the four: the Reynolds number, the Smith number, the Sherwood number, and the Stanton number. But there is a problem, or there are problems actually that uses the JD factor that is given in the problem. That way, they can get the, let's say for example, the expression for this, the Sherwood number, the Reynolds number, and the Smith number through the use of this dimensionless J sub D factor. Now, in mass transfer, considering various geometries, we are to, as I've said in the beginning of the slide, we are to look into the type of flow. And the first type of flow that we're going to discuss here is the flow inside pipes. And the flow inside pipes can be again divided into two types of flow. That's the laminar flow and the turbulent flow. So we're going to discuss first in here the flow of fluids inside pipes, which is laminar. So when a fluid or a gas is flowing inside a pipe and the Reynolds number is below 2100, then we have laminar flow. Now, experimental data obtained from mass transfer from the walls for gases are plotted in figure 7.3-2, and the figure is shown below, for values of W divided by the molar diffusivity times rho times L less than about 70. So this particular figure is for this value of W over DAB rho L, which is less than 70, or it's just 70. The ordinate in this particular figure, or that's the Y ordinate, is Ca minus CaO over Cai minus CaO, where Ca is the exit concentration of the gas, CaO Ca is the exit concentration, CaO is the inner concentration, and Cai, take note, is the concentration at the interface, and that's between the wall and the gas. So the interface of mass transfer, that is. Now the dimensionless abscissa, this one, can either be W over DAB rho L, or it could be a combination of the Reynolds number multiplied with the Smith number to the D over L ratio and the pi over 4. Now, your W here is the flow in kilogram per second, and L is the length of the mass transfer section in meters. So the rest we have defined already in terms of the two dimensionless numbers that appear. But does this mean that if you don't have the information for this, you can utilize this particular expression for the abscissa? That way, if you have already chosen the appropriate curve to use in here, we only have two, one for rod-like flow and the other for parabolic flow. We can project that particular value until we reach the curve and read the value of the ordinate, which will lead us to the concentration that is being sought in the problem. And most of the time, that concentration is the exit concentration in the pipe. Now, since our experimental data follow a rod-like flow inside pipe, so our fluid element, if we cut through it, if we cut through a fluid volume, its shape is that of a rod. Then when you have already the value for the abscissa here after computation, then you are to project until you reach the rod-like flow curve on top. And then you read on the left side the corresponding value for this set of variable and given information. The velocity profile is assumed fully developed for parabolic form at the entrance. So this parabolic flow curve will only be used if this statement is stated in the problem, and that's the velocity profile is assumed fully developed at the entrance. Now, for liquids that have small values of molar diffusivity, data follow the parabolic flow line. So, if you think that the molar diffusivity value is small, or if the problem says that it's already considered small or negligible, then you can use the parabolic flow curve on top. Now, still, your abscissa would still be this one, but we expect that the value of the W over DAB rho L, or this NRE, or Reynolds number, Smith number, D over L ratio, and pi over 4 would now be over 400. Unlike if it's just the usual case wherein our molar diffusivity is not assumed to be very small, and this particular value for the abscissa will not go beyond 70. But if it's higher than that, so even beyond 400, then you can use the data which is for the parabolic flow. So the value that you're getting here should be projected until you reach the parabolic flow curve. Then, of course, check on the left side on the vertical axis the corresponding value that you will equate to this set of variables and parameters. Now, so that's for laminar flow inside pipes. So for turbulent flow inside pipes, meaning your Reynolds number is above 2100, we're still considering gases and liquids. This will be the Reynolds number. This will be rather the dimensionless number that you're going to use, the Sherwood number. And it relates now your convective mass transfer coefficient to the diameter and the molar diffusivity of your solute to your fluid. Equal also to this expression, equal also to this expression. This one is your Reynolds number and this one is your Smith number. Now, the equation holds for a Smith number, this last expression here, of 0.6 to 3000. And this is the note that Smith number for gases in the range of 0.5 to 3. And for liquids, it's above 100. So for gases, we expect that our Smith number here will be on the range of 0.5 to 3, whereas for liquids, it's above 100. Or that is probably the reason why we have the above 100 here in general. The phrase above 100 in general. So this particular dimensionless number, the Sherwood number, gives you the, or tells you of the convective mass transfer coefficient, or if it is already given, then you already know the Sherwood number. So this is for turbulent flow. For laminar flow, then you have, for laminar flow, you have this particular scenario. This one, you are to use this particular graph for laminar flow. Okay, so for us to be able to apply what has been discussed here regarding flow inside pipes or cylinders, whether laminar or turbulent, we have this particular sample problem. Now, in this sample problem, you're given a tube which is coated on the inside with naphthalene and has an inside diameter of 20 millimeters and a length of 1.10 meters. Now, air at 318 Kelvin and an average pressure of 101.3 kPa flows through this pipe at a velocity of 0.80 meters per second. Assuming that the absolute pressure remains absolutely or essentially constant, calculate the concentration of naphthalene in the exit air. So the sample problem is very clear that your air here is flowing inside a cylinder. So that would be a pipe. It has a coating of naphthalene. So we expect that the naphthalene coating of the pipe, of the inner part of the pipe, will be diffusing to the air that is flowing inside the pipe. So we need to illustrate properly what's happening in this problem so you would fully understand, even though it's just a matter of substitution to a set of formula. So for the given in this problem, let's say you have this pipe and this pipe has an inner coating. This coating is naphthalene. And this being our solute, so we will label as A. So the inner diameter of the pipe is 20 mm and the length is 1.10 meters. So as discussed in our set of slides, the concentration at the entrance of the fluid that is entering the pipe is labeled as CaO. At the exit, it's Ca. Now, we have air entering. And this particular air has the following information as it enters our pipe. So, it's at 318 Kelvin with a pressure of 101.3 kPa and a velocity of 0.80 meters per second. Now, the pressure is essentially constant, so this is a constant during the entire process of the air flowing inside the pipe. So, this is the given information in the problem. So, we go now to the required information. So, the problem requires us for the Ca. The concentration of the air as it leaves the pipe or at the exit part of the pipe. So, our diffusion here actually is from the naphthalene. So, this is the direction of the diffusion from the naphthalene coating inside the tube to the air that is flowing inside. Now, based on what we have discussed, we need to first know the type of flow. We need to know the type of flow that is stipulated in the problem. So for us to know whether the flow is laminar or turbulent, there's a need for us to determine the Reynolds number. So our Reynolds number is diameter times the velocity times the density over the mu. Now this is for our, actually this is for our fluid. The Reynolds number is based on our fluid. So for air, since our air is at 318 Kelvin, you are to look for the value of the raw and the viscosity from the appropriate property table or the appendix from a particular book. So your density for air is 1.114 kilogram per cubic meter, and for your viscosity you have 1.932 times 10 raised to negative 5 pascal second. Now knowing that, you can go back to the formula and substitute the value. So for our diameter, we have 0.02 for it in meters. The velocity is 0.8 and the density is 1.114 and the mu is 1.932 times 10 raised to negative 5. Now this will give us a Reynolds number equal to 922.6. So from here, since it's below 2100, the flow is laminar. If the flow is laminar, there's a need for us to use the table, or rather the figure for laminar flow. And what that figure is the one that I have discussed to you a while ago. Now, after this, we will go to determining since in that particular figure, aside from the Reynolds number, you will be needing the Smith number for the abscissa. In that figure, we have X, the abscissa, being equal to the Reynolds number times the Smith number times the ratio of D to L and times pi over 4. This is the abscissa for that particular figure. Then there's a need for us to determine the Smith number, or this is SC. Now, for now, we cannot yet determine this abscissa value because we still don't have the Smith number. So, for the Smith number, and by the way, the reason why I got this wrong is I wrote the capital letter S. So, this should be N. It's a dimensionless number, and this Smith number is equal to the mu over the rho times the molar diffusivity of naphthalene in air. So naphthalene is going to diffuse to air, so we need its molar diffusivity. Now, from a previous problem and table, we have taken the molar diffusivity of naphthalene. So I will leave that to you. It was discussed in the previous topic on diffusion. So your mu in this case would still be used. So that would be 1.932 times 10 raised to negative 5. And we have the density to be 1.114, and we have the molar diffusivity, which is 6.92 times 10 raised to negative 6. So you will have a Smith number now equal to 6.92 times 10 raised to negative 6 meters squared per, this is your, they copied this one, this would be your molar diffusivity. So the answer, after we have already made use of the molar diffusivity value, will be 2.506. Now, from equation 1 on top, you can solve for the abscissa value for figure 7.3-2. So, for the abscissa value of that particular figure, we have now the Reynolds number, which is 922.6. We multiply it to 2.506. We multiply it to the diameter, which is 0.02, the length, which is 1.10, and of course we have the constant pi over 4 at the last part of the formula. The abscissa value for that figure is 33.2. Okay, that's 33.2 for the abscissa value. Now, if we go back to our graph, I'd like to show to you the graph for laminar flow. This is the graph class, and we have already determined the abscissa. The value of it is 33.02, and we are to project from that particular value of 33.0 up to the rod-like flow. Rod-like flow here, this particular curve. So if you're going to go up to that, your y value will be more or less, since this is 10 and we are 33, this is 100, this must be 50, this must be 25, so 33 is somewhere here. 20, 15, 150, 25. So we are on 33, so somewhere here. We go up until we reach here. More or less this part here. So actually the value for the coordinate will depend on your reading. So if you're going to look at it very closely, if this is 10 raised to negative 1, this would be 0.1. This is 0.1 and this is 1. And this is 0.5. This is 0.5 here, and this is 0.75. So that's how you're going to read it. Okay? So more or less a y value from this particular graph could be read and substituted so that we can substituted for the ordinate so that we can solve for the concentration. So let's say our y read from the figure, your y, which is CA minus CAO over CAI minus CAO, in the figure is more or less 0.55. Then we will substitute the initial concentration that is given in the problem, and that's the inlet concentration in this case, and the boundary concentration in the interface, so that we can solve for the C at the exit. Now, this is our equation 2 for now, since we still need to determine your CAI. Okay, so we only have so far equation 1. So for our equation 2, this would be this. Now, for CAI, you need the partial pressure at the interface divided by the product of R and T. The partial pressure in the interface, in this case, will be the vapor pressure of A. This would be measured at 318 Kelvin. Because A is going to diffuse, the naphthalene is going to diffuse to your air. So for that, now in this case, the partial pressure of naphthalene, or that is the pure vapor pressure of naphthalene, was not given in the problem, that we can refer to a previous example wherein naphthalene also is the one diffusing to a particular fluid, and that is also air. So at the given temperature of 318 Kelvin, the pure vapor pressure of naphthalene, which will also be considered as its partial pressure at the interface, is 0.555 millimeters mercury. So we need to convert that to Pascal so that it will agree with the rest of the units that we're using, and the equivalent of that is 74 Pascal. Go back here to the formula and solve for the concentration of air in the boundary. So that would be 74 divided by 8314 times 318. So you will have a value of 2.799 times 10 raised to negative 5 kilomole A over cubic meter. Okay, kilomole A per cubic meter. Now we have already the CAI, then we can solve for the CA, the exit concentration. So you will have 0.55 being equal to CA minus the concentration at the inlet is 0, and our CAI is 2.799. You can make it as 2.8 times 10 raised to negative 5, and this is still a 0 because this is CAO here. So now you will have a value for CA which is equal to 1.539 times 10 raised to negative 5 kilomole of A per cubic meter. So this is the corresponding concentration of naphthalene at the exit part of the pipe. Now this particular sample problem illustrates the use of the dimensionless numbers and the table and the figure for determining the concentration. Now this particular concentration will not be limited only to the exit concentration. It could be concentration at any point in the pipe. All you have to do is change the L here. So if it's somewhere in the pipe, like only halfway through the pipe, then this should be changed, and that would be the concentration at that particular point. In this case, we made use of the entire length of the pipe because we are after for the concentration at the exit. Okay, so our next topic will be for flow outside solid surfaces.